x I cap minus 2y square z plus z square k, and on the surface z equal to 0, z value is always 0 for every point there. So you simply put z equal to 0 for the bottom surface. The bottom surface S1, for bottom surface S1, z value is always 0. So your A vector here is this, because for every point on the bottom surface, z value is 0. Then when you take the dot product A vector dot n cap, your n cap is minus of k here. So I cap dot k cap is 0, j cap dot k cap is 0. Therefore, this integration or the flux of the vector field across the bottom circular surface will be 0. The bottom circular surface will be 0. Now, over here, let us look into the top surface here. So the top surface s equal to 2, sorry, z equal to 3. So I have already shown you the top surface here. The top surface is the circular surface on the top of this cylinder. Here the equation is z equal to 3, because at every point here z value is 3. And the unit vector is also k cap. I already discussed that. Then here instead of z, if you put 3, then 3 square is 9. So a dot n will be this, and you will get 9 here. So then you calculate the flux across the top surface, that is S2. The flux across the top circular surface, that is across surface S2. Then your a dot n cap is 9. So 9 is a constant, you can take it out. So you have to integrate this surface element ds2 over the surface S2. So over here, as I was telling you, this ds2 here is your ds2 here is a surface element here. By integrating ds2, by performing integration, surface integration of ds2 here, by performing surface integration of ds2 over the whole surface S2, over the whole surface S2, it simply means that we are summing up ds2 element over this whole surface. You are summing up all the surface element, on this circular surface. So eventually it will result in area of the circle here. It will result in area of the circle here. You just assume that there is a circular surface here, as you see here, and your ds2 is infinitesimally small area element here. So all this this particular circular surface can be divided into large quantities of segments of this ds2. Now integration means you are summing up all those small, infinitesimally small area segment, infinitesimally small segment of that particular whole area. If you sum up all of this, then it will result in area of the circle here. Area of the circle, as you know it, it is pi r square. Your radius is 2. Okay, so this again is simply this is simply area of the circle with radius 2. Now area of the circle with radius 2 is pi r square, r is 2, so 2 square is 4, 4 into 9 is 36, so you have a 36 pi here. Now we have the last surface, that is S3. On S3, that is the curved surface, your equation is x square plus y square is equal to 4. So in order to find unit vector normal to the surface, x square plus y square equal to 4, like I was explaining here, the equation of any surface, arbitrary surface, can be represented like phi equal to c if phi is a function of x and y and z. Then here your phi is, what is your phi? Your phi is x square plus y square. What is your c? Your constant is 4, right? So grad of phi will give you a vector perpendicular to the surface, perpendicular to the curved surface. So grad of phi, you can calculate grad of phi like this. So there is a typing error here. My bad actually. there should not be any dot here. Okay, this dot has to be removed. There is no dot product here. When you are taking the grad of phi, the dot term has to be removed. Please consider this like when you are studying this, do not consider this particular dot term here. There should not be a dot. There was a typing error here and there. So when you take the gradient is the operation of the vector operator on a scalar function. So you, dot or cross product is not applicable. Dot and cross product is applicable only between two vectors. So one of them is scalar, means there is no dot product. So we have to remove this. Now, when you take the gradient here, you are differentiating x squared plus y squared with respect to x squared plus y squared with respect to y, x squared plus y squared with respect to z. Differentiation of x squared with respect to z and y squared with respect to z will be 0. So the third term is 0. And if you perform differentiation of x squared is 2x, x square y square with respect to x will be 0, and similar differentiation of x square with respect to y is 0, y square with respect to y will be 2y. Therefore your gradient will be a vector like this. Now in order to obtain the unit vector along any vector, what you have to do is you have to divide that vector with its magnitude. You have to divide that vector with its magnitude. So then using this expression, you can obtain unit vector perpendicular to the cylindrical surface. So this gradient of x squared plus y squared is 2xi plus 2yj cap, and the magnitude is square root of 4x squared plus 4y squared. So when taking the magnitude, your unit vector, you just the coefficient, you just square the coefficient of each of this unit vector. The coefficient of I cap will have to be squared. That is 2 square is 4, 4x squared plus 4y squared. And you know that when you take a 4 as a common factor and there is a square root here, so when you take it out of this common factor square root, it will become 2. And 2 and 2 will cancel out. And again, the equation of your circle is x squared plus y squared equal to 4, and square root of x squared plus y squared will be equal to 2. If you take square root on both sides, x squared plus y squared will be equal to 2. So here you will find that square root of x squared plus y squared is 2. Square root of x squared plus y squared is 2. So x has to be divided by 2, y has to be divided by 2. So this vector is your unit vector. Now you have to again take a dot product with your a vector. Your a vector on the curved surface is z value is no longer constant. On the curved surface, z value is no longer constant, unlike the bottom and the top surface where z is 3 and z is 0. So when you take a dot product with this, I dot I is 1, I dot j is 0, j dot j is 1, j dot other things are 0. So k dot I is 0, k dot j is 0. So simply what you will be getting here is 2x square minus y cube. If you take this, you will get 2x square minus y cube. Then now you have what is called your now you have your a dot n cap here. So your purpose was to perform surface integration over S3, to perform surface integration over S3 like this. This is what you are trying to get. Vector a dot with n cap d as 3. So from this a dot n, you already have your a dot n here. Now you have to integrate over ds3. So as we know it, this surface S3 is a curved surface. So if it is a curved surface, it is easier to perform integration using what is called polar coordinates. Polar coordinates, I will discuss this thing in detail later on. So in polar coordinates, we can represent any point on the coordinate system like this. If you have something like this, so this is your x-axis. Suppose you have any point here. This, let's say this is your theta here. Let's say this is your theta. Your x component will be, let's say this is the radius, the distance of this is, let's say the length of this is r. The length of this is r. So if you take a projection on the x-axis, this is your x component. This x value will be r cos theta. If you take a projection on the y-axis here, the horizontal axis is your y. This is your y. So this projection, this length, that is from this to this, this length will be your r sine theta if you follow the trigonometry. So that is how you are writing using polar coordinates. Your r value, the radius here in our problem, radius value is 2. So it is 2 cos theta, 2 sine theta. Okay, x is 2 cos theta, y is 2 sine theta. So by writing x as 2 cos theta and y as 2 sine theta, I can convert my Cartesian coordinates, that is Cartesian coordinates, into polar coordinates. Now, in order to obtain the surface element here, the surface element on the surface here. So wait. So here you see that there is a surface element here. This is surface element of the curved surface. You see what I'm drawing here? On the curved surface, you have a surface element. So how do we write this surface element in terms of polar coordinates? That is our objective here. Okay. So in order to do that, we consider a small increment along the theta coordinates. Polar coordinates means r and theta. We'll talk about cylindrical coordinates. So r, theta, and z will be your cylindrical coordinates. So this is your theta. So small increment in d theta value is called d theta. Small increment in theta value is called d theta. And d theta is considered to be very, very small. D theta is considered to be very, very small. So when you are writing tan d theta, tan d theta, tan d theta in Taylor series expansion, tan d theta, the first term will be d theta minus second term will be d theta cube, d theta cube upon 3 factorial or something like this. Okay, d theta minus d theta cube upon 3 factorial plus d theta to the power 5 upon 5 factorial. So this Taylor series expansion you must have studied. So here, if we consider infinitesimally small increment or small angle d theta here, the higher order terms like d theta cube, d theta to the power 4, to the power 5 and all, the higher order terms will be negligible because there will be 3 factorial, 5 factorial in the denominator. So tan d theta will be equal to d theta. So tan d theta, what is tan d theta? Tan d theta is opposite upon adjacent. When you are writing infinite small volume element, you can consider when you are considering infinitesimally small increment in angle d theta here, you can assume any of these as 90 degree. If you consider infinitesimally small angle d theta here, any of this can be considered as 90 degree, and the opposite surface will be this. The opposite surface will be this, and one of these you can consider it as adjacent. So opposite surface, if I consider this as opposite surface as your, for example, gamma, then your tan d theta will be opposite gamma upon adjacent. What is adjacent here? Adjacent is simply the radius of a circle. The radius of circle is 2. Adjacent. tan d theta will be gamma upon 2. And tan d theta, due to small angular approximation, higher order terms can be neglected. Tan d theta can be written as d theta. So your gamma will be equal to 2 d theta. 2 d theta. 2 d theta is this arc here. The length of this arc here will be your 2 d theta. Your gamma here is this length. This length will be your 2 d theta. And as we are considering cylinder, the z this axis is your z axis. So if you consider small increment also along the z axis, this 2 d theta into dz, 2 d theta into dz will be your surface element ds3. If you try to deduce it yourself also, I think you will arrive at this. What I mean to say here is that the surface element on the curved surface, that is your ds3, will be 2 d theta into dz. 2 d theta into dz. Okay. So instead of ds3, we will write 2 d theta into dz. Instead of x, we will write 2 cos theta. Instead of y, we will write 2 sin theta. So following that, you can perform this integration. That was like your a dot n was 2x squared minus y cubed. So instead of x, 2 cos theta. Instead of y, it is 2 sin theta. Instead of ds3, you are writing 2 d theta dz. And that what will be the limit for z axis? What will be the limit for z? What will be the limit for theta? You see that in order to perform the integration over the whole curved surface here, z value has to go from z equal to 0 to 3. And in order to perform over the whole circular surface, theta value has to go from 0 to 2 pi. Okay, so that is what you have to consider. Your purpose is to cover the whole surface. So theta goes from 0 to 2 pi, z goes from 0 to 3. Then you do the integration steps here, all these things, you will arrive at 84 pi. Then if you add the right hand side, the bottom surface, the integration was 0. On the top surface, it was 36 pi, and then 848 pi. And then together you will get 84 pi, and which is exactly same as the left hand side here. The left hand side here, what is that? The left hand side value we already obtained 84 pi, as we already obtained as the left hand side. So on the right hand side also you will get the 84 pi. So that is how you have to verify the divergence theorem. So I think I will stop here. You please work out all the steps like I discussed, and if you have any queries, tomorrow we can